Technically, we've covered all the important terms with our electrostatics. We've had force, we've had field, we've had energy, and we had voltage, and we did lots of problems to see how to apply them. But there's one more idea I'd like to take a deeper dive into, and that is our idea of voltage. There's a few things about voltage that can make life easier that I'd like you to know about. First of all, I want to make sure you know that the term voltage is sometimes referred to as the term potential. Okay, so if you ever see them, just say potential. Not potential energy, but just the word potential. That refers to voltage. And if you look at the voltage in one spot compared to the voltage in another spot, that is the delta voltage, they'll sometimes call that potential difference. Again, it's not potential energy, it's potential, it's voltage, it's delta V. All right, so if you see potential difference, that is delta V. Remember, if you want to turn it to energy, you have to multiply by how much charge moves from place to place. Okay, so we looked at our sensor, and we looked at what the voltage was, and then we moved our sensor to a new location, and we found a new voltage. The thing that we'd like to make sure we understand is this is not the only place I can put this sensor to have this voltage. Any place I put it that has that same distance will have that exact same voltage. So because there are so many different places that all have the same voltage, they came up with a new idea, a new term, a new way of looking at things, and that is what's known as an equipotential line. Equal voltage, equipotential. Again, potential means voltage, equi means equal. So an equipotential line are all the points in a plane that have a given voltage. So if you look, everywhere along this red line has the exact same voltage of 10. Everywhere on the blue line has a voltage of 20, and everywhere on the purple line has a voltage of 30. So equipotential lines are all the places that have the same voltage. It's not so exciting for just a single charge. It's not so useful for just a single charge. Its real usefulness comes in is when we plot them out for a distribution of charges. That is, two or more charges. So here I have charge 1 and charge 2, and I drew out the equipotential lines. I had Desmos do this for me. So everywhere along the red oval is a spot that has a total of 10 volts. You'll notice that these shapes can get pretty crazy looking, but they are a great way of getting a sense of where the voltage is high and where the voltage is low, and more importantly, where the voltage is changing rapidly and where the voltage is changing gradually. All right, so if you look, places where the lines are close together are spots where you have a rapid change in voltage. So if you move the charge from one of those to another, you would have a rapid change in energy. The other thing to realize is that when you walk along an equipotential line, you are not changing voltage, which means you are not changing energy. So it takes no effort to move a charge around a single equipotential line. Think of equipotential lines a lot like the lines on a contour map. So these are lines of elevation. They serve the same function as the equipotential lines. These are lines of equal elevation. So everywhere along this line represents an elevation above sea level of 1,000 feet. Everywhere along this line represents an elevation of 1,500 feet, and so on. Where the lines are close together represents places where the elevation is changing quickly. It means that it's steep. Anytime you walk along an equipotential line, it means you're not changing elevation. It takes no real effort to walk along one of those lines. The greater effort is when you're walking perpendicular to those lines. Okay, so that is how you can think about equipotential lines around charges. They're just like the contour lines on a map. These spots in the middle would represent the highest points on the mountain. Okay, so you can see that our elevation is getting higher and higher and higher, and the highest point would be in the center of those last contour lines. Here is one where there are actually a bunch of different peaks. So you'll notice there's a local peak here, and here, and here, and then an absolute maximum in the center of this big series of contour lines. So this is Mauna Loa volcano on the island of Hawaii, and this shows the profile in terms of elevation for that location. And again, areas like this are not changing in elevation that rapidly. That would be a good place to put an ice skating rink. Of course, Hawaii is not a great place to do that, so maybe a soccer field. Okay, you would not want to put your soccer field where these lines are really close together, because that would represent a very steep incline. Okay, so if it says how much energy would it take to move a proton from the red line to the purple line? So easy. You do change in voltage. So in this case, it's 20 volts. And then you know your energy is equal to your change in voltage times your charge. So you simply multiply your change in voltage by the charge of the proton. Super, super easy working with these equipotential lines. Okay? If you wanted to know how fast it would be moving, you would take that change in potential energy and set it equal to your kinetic energy. All right, that's it. I have a Google form online for you to try and make sure that you understood all these main ideas. And I also have a link to a Desmos where you can change around the charges and the locations to watch how these equipotential lines vary as you vary different parameters.